We know that redox reactions involve a transfer of electrons, but is it possible to actually use these electrons to do some useful work? Yes, it is. We can actually do these by using a combination of galvanic cells. Galvanic cells consist of two half cells. Each one of these usually contains a metal and a metal in solution. So in this case we have zinc metal dipping into a solution of zinc 2+, and copper dipping into a solution of copper 2+. These are connected to each other by a wire, which in this case is running through a globe, which would let electricity pass from one to the other. To complete the circuit, we have to put in a salt bridge, which goes across between the two liquids. It's usually soaked in an unreactive substance such as potassium nitrate or sodium nitrate or something like that. Once that is in place, when the electrons flow from the zinc to the copper, they travel through the wire and electrical neutrality is maintained, because as the copper 2+ ions come out to accept the two electrons, then potassium ions will go into solution to replace that positive charge which is being removed. On the other side, zinc metal dissolves to form zinc ions in solution, which increases the positive charge in that solution. So the negative nitrate ions will come down from the salt bridge to neutralise the extra positive charge that's being formed. So in this case you can see the electrons are actually travelling through the wire to get to the copper. So if we put a device in the way, such as a lamp or a voltmeter or something like that, we can actually use the electricity which is being transferred. The reaction between zinc and copper 2+ is a spontaneous reaction. As long as we have an electrical circuit that allows the electrons to flow from one to the other, this reaction will actually occur. By definition, we describe these two pieces of metal as being electrodes. The anode is the electrode where the oxidation reaction occurs, where the zinc is losing the electrons. The cathode, on the other hand, is the electrode where reduction is occurring, and in this case that's where the copper 2+ is gaining electrons, so that's the copper electrode. We already have an acronym, oil rig, which is our oxidation is loss of electrons, reduction is gain of electrons. If we add another two letters in there to make the acronym, we can have that oxidation occurs at the anode, so the AT is the anode, and reduction occurs at the cathode, the CAT is the cathode. So that will help you remember. We can use all sorts of different combinations to make these galvanic half cells. In this case we have some copper dipping into copper 2+ solution, and over on the other side we've got some iron 3+ and iron 2+. Both of these are aqueous solutions, so we actually need to have a metal electrode, so we use something that's relatively inert like a platinum electrode. Now when we look at this, we can see that in the copper half cell there are two possible reactions that could occur. The copper 2+ could gain electrons, or the copper metal could lose electrons. On the other side we have the iron 3+ could gain an electron, or the iron 2+ could lose an electron. So how do we know which one of these reactions is actually going to occur when there are so many different possibilities? Is there a way of telling? Well, yes, there certainly is. You remember in earlier years we had an activity series which showed which metals were reactive and which ones were not so reactive. Potassium was at the top of our series, and something like gold and platinum was down at the bottom. This really shows the ability of potassium to form potassium ions, in other words to lose electrons. However, conventionally, when we're talking about galvanic cells, we use the reduction half equation rather than the oxidation half equation. In other words, the ability of the metal ion to gain an electron. In other words, it's going to be reduced. That means if it's being reduced, it's acting as an oxidant. So the table is arranged with the strongest oxidant at the top and the weakest oxidant at the bottom. So effectively, we've turned the activity series upside down. So we have gold at the top, which is our strongest oxidant, the one that really wants to become a metal, and the reactions occur between strong oxidants and strong reductants. So on the top left-hand side, a species will react with something which is on the bottom right-hand side. And of course we assume that all these reactions are occurring at standard temperatures and pressures. Remembering that there are two possible reactions that can occur in each half cell of a galvanic cell, we can use the electrochemical series to predict which one is actually going to be the reaction that will occur. Two steps need to be taken. First of all, we need to identify the position on the electrochemical series of each one of those cell pairs. So for instance, the silver ion silver pair is high on the electrochemical series, the copper 2 plus copper cell is low down on the series. The pair which is higher on the series is going to be undergoing reduction, and the pair which is lower down on the series will be oxidized. So in practice, if we have the example of the silver and copper, silver ion is higher on the electrochemical series than is the copper, and so it's the silver that's going to gain its electron, and it's the copper metal which will actually be oxidized and lose its electrons. So to work out our overall equation, we just need to leave the silver plus electron to give us silver half equation, and we reverse the copper equation so that the copper is actually losing the electron to form copper 2 plus. So how do we work out the overall equation for the reaction? We've already established that the silver plus ion is going to react with copper, because the copper is going to lose electrons and provide it for the silver. So our first reduction half equation is the silver ion going to silver metal. The oxidation equation will be the copper going to copper 2 plus. But when we look at the electrons, we see silver needs 1 and copper is going to give 2. So we need to multiply that first equation by 2. Then when we add all those two half equations together, we can see we've got the 2 electrons on both sides, which cancel out, giving us our overall equation of copper with 2 silver ions to give a copper ion and 2 silver metal atoms. So now a few practical examples to see how this works. So if we want to predict these reactions, let's have a look at a couple. We've got iron 3 plus with silver ion. Can this reaction actually occur? So the first step we have to do is to locate the species on the electrochemical series. We can see that the silver plus ion is higher than the Fe3 plus ion, so the silver ion is going to be the one which is reduced. To react with it, it needs to react with something on the right-hand side, which is the Fe2 plus ion. Well, in our particular equation, we've got the Fe2 plus ion on the right-hand side, so this reaction is not going to occur. What about this one? Chloride and H+. Will that reaction occur? First, we need to find those species on the series. We have chlorine at the top and H+ is lower, but the chloride ion, which is our reactant species, is on the right-hand side, so this reaction isn't going to occur either. What about the next one? Copper and zinc 2+. Find those on the table. Got copper 2+ and zinc 2+, so according to our rule, the copper 2+ should react with the zinc metal, and we have the equation exactly reversed, so this reaction isn't going to occur either. What about the next one? We still have the same species, but this time we've got our copper 2+ at the top, we have our zinc down low on the right-hand side, so this reaction is actually going to occur. So, as a final example, will solid nickel react with aqueous lead? First step, we need to find them on the electrochemical series. There are our 3 reduction half equations, and we can see that the lead 2+ is higher on the series than the nickel 2+. So therefore, we can predict that lead 2+ would react with solid nickel. So the strong oxidant lead 2+ reacts. So our equations will be that the nickel releases 2 electrons to give nickel 2+, that's our oxidation half equation, and the lead will gain those 2 electrons and become solid lead. If we look at our electrons, nickel's losing 2, lead ion is gaining 2, so our overall reaction is just going to be nickel solid plus lead 2+ ions to give us nickel and lead.